Okay, so welcome to Math 140. This is, I believe, lecture 31. So we are at the home stretch now in terms of the semester. As always, if there's material you want me to cover and go over, just let me know. What I want to do is I want to use some of the last few classes to give you a little bit of a sense of what can you do with the material that we've been learning and what might come next if you continue. Most of you are not going to become professional mathematicians. It's absolutely fine. But hopefully you'll have a sense of what math can do and how it can help you attack a variety of problems. One of the most important things in the 21st century is to have some kind of pattern recognition. Hey, this looks like something I've seen before, which means either you know where to go to find out how to do it, or you know what kind of questions to ask somebody who might then know how to do it. One of my greatest successes is a physics professor here years ago, Bill Wooters. Came to me with one of his students with a project that they were doing, and they needed help with certain exponential sums. And I was able to do a little bit, but what they needed was extremely complicated and technical, well beyond my ability. But I actually know somebody who wrote one of the classic books on the subject, so I'll make an introduction. So I send it to him, and he goes, "Oh, no. You need God for this. You need Nick Katz. He's the only one." And so he passed it on to Nick Katz, who then wrote a 50-page paper titled "On a Question of Roots." And this is how the network goes. You don't need to know how to do something. You need to know enough to recognize, what is this? How could I push this to whoever has the knowledge to do this? And that's why it's so important to get a sense of what can and cannot be done. And so I want to talk today a little bit about difference equations, which are discrete versions of differential equations. And thus, not surprisingly, the next class will be on differential equations, right? And so we will analyze one of the most important battles in world history, the Battle of Trafalgar from the Napoleonic Wars. So if any of you have seen that in a history class, the first time I taught this, I actually had somebody who was doing it in a history class at Williams. We will look at the battle from a slightly different perspective than you would in a history class. But it's interesting to see how can math be applied. Right. So I want to talk a little bit about Fibonacci numbers today, talk a little bit about generating functions, and then as an application, and you watch a video on why you should not use the knowledge I'm about to give you to go to Las Vegas to gamble. Again, I love teaching, but if it was guaranteed to make that much money, I'd be there. So there's got to be a flaw. And so many times people are convinced they have the solution. Occasionally, yes, occasionally they find something that's been missed by people for centuries. But odds are there's a reason no one else is doing it. And I still remember as a little kid, my dad wrote a computer program in BASIC to just try to implement double plus one, because he goes, wait a minute, this sounds really good. What is the probability that things would fail? And he didn't know how to calculate the probability, but he knew how to simulate it. And with just a few minutes of code, he goes, so that's why people don't do it. Okay. And so again, so this is the game plan, is to give you a sense of how can we use the math that we're developing. Differential equations model a tremendous number of things in the real world. They are equations where the parameters vary continuously in time. So we're going to start by looking at things that vary discretely, discrete time steps. Think of this as the old compound interest problems, where the interest is compounded maybe once a year, or once every 6 months, or once every month. And then in the limit, you get the compounded continuously. If your system is sufficiently large and complex, you can probably approximate a discrete system with a continuous one. Births of human kids, continuous or discrete? I would say this is a discrete event. But when you look at how many people we have in the world, I think you can reasonably model this as a continuous process with independence. Okay. Did we have a homework today looking at some fractions? Yeah. So we had, and so there's almost surely some reason behind that. All right. So what I'm going to do is I'm not going to spend too much time on this, but I've put in the notes a couple of different types of problems you can do with recurrence relations and whatnot. There's a lot of really interesting ones. We'll talk a bit about Benet's formula in a bit. This is one of my favorite formulas in all of mathematics. It's an explicit formula for the Fibonacci number. So we'll talk about the Fibonacci numbers in a bit. A couple of other more beautiful ones that we're not going to really get to. All right. So let's start talking about the Fibonacci numbers. So hopefully you've seen the Fibonacci numbers before. So they're defined as each one is the sum of the previous two. And you need to give some initial conditions. And there's a bunch of initial conditions you can do. This one I'm doing it as 1, 2, 3, 4, 5. Other choices is F0 equals 0, F1 equals 1, F2 equals 1, F3 equals 2, F4 equals 3, ... So depending on what you're doing, one definition might be a little bit more convenient than another. And this is, a problem you always have in science. Depending on who's doing things, sometimes one notation is a little bit better than the other. So the advantage of the 1, 2, 3, 4, 5 is if you use this, you get a beautiful theorem that every integer can be written uniquely as a sum of non-adjacent Fibonacci numbers. If you start off with 0, 1, 1, well, you're not going to be able to get uniqueness because you have two different ones. So I could write my number, 6 as 1 plus 5, or 1 plus 5 using two different ones. So for decomposition purposes, it's cleaner if the Fibonacci numbers go 1, 2, 3. But for a lot of other things, it's nice to start 0, 1, 1, 2, 3. If you had to find the 10th Fibonacci number, could you do it? If you continue the list, 0, 1, 1, 2, 3, 5, what comes next? 8, then 34. This isn't that hard. What if I asked you for the millionth Fibonacci number? What if I told you your entire college grade depends on calculating the millionth Fibonacci number? You have 4 years. No computers allowed. 4 years. Okay, now, what is the danger of making algebraic mistakes somewhere in those 4 years?
It's not.
So if I were to do this, I would actually do the calculations in base 2 rather than in base 10. So do you know what base 2 is? Base 10 is using the numbers 0 through 9. Base 2, I would write a number as, say, an times 2 to the n plus an minus 1, 2 to the n minus 1, plus a1 times 2 plus a0. Each ak is in 0. So if I write my numbers in base 2, the algebra is a lot easier. 1 plus 1 is 0, carry the 1. 1 plus 0, 0 plus 1 is 1. 0 plus 0 is 0. I think I'm much less likely to make mistakes in base 2, but my numbers will be longer. Absolutely fine doing that. But again, the danger of making one mistake somewhere. I wish I had the power to make this an option for you. All right, so let me go to some space in a mathematical notebook. So the first question is, how big is the nth Fibonacci number? So Mathematica, I believe, that's the Fibonacci command. So 0. So it starts off with a 0. So what I can do is I can see how long it takes. Here's the 10,000th Fibonacci number. That was basically instantaneous. 10,000th Fibonacci number. It's kind of big. I just want to see how long it took to do it. And it's basically doing it, the fact that it's saying 0 is it's basically doing it instantaneously. Here's the 1 millionth Fibonacci number. And it is displaying it. So here is the 1 millionth Fibonacci number. Let's get a sense of the size. I always forget how Mathematica does things. So the log of base 10 of 100 should be 2. So I'm going to take the log of base 10. G, 1 million. So the millionth Fibonacci number has a little over 200,000 digits. So and then of course you have to add, well, how many digits do I have? So you can try to do the calculation. Do you think you can do this in 4 years? So how many seconds are there in a day? There's 3,600 seconds in an hour, right? 24 hours in a day, right? 365 days in a year. 365.25, because you'll get at least one leap day as we go through all of this. And we don't have to worry about the years that are multiples of 200, because you're not going to be in college that long, right? So will this give us how many seconds you have? Oh wait, now we have to multiply by 4. You have 4 years in college. So it's about 10 to the 8. And what we had above was like 2 times 10 to the 5th. But remember, we have to sum all of these numbers, right? In terms of the number of digits. So what if I take this, just try to get a sense of sum from 0 to 1 million. Oh, there's a mixture. I'm just adding right now all the Fibonacci numbers from 1 to 1. And this is where you want to know the timing. This is just how long it's taking. And so when I'm writing the code like this, I have no sense of how long it's taking. I could make this program a little bit longer and print every 1% that I've done 1%. So I just have some rough idea of how long it's taking. So now let me try putting back the I mean, it was definitely trying to sum it before. I do not understand why it is not. All right, well, we know the last one has 208,000 digits. What I can do is I can look at, I'll just cheat a little bit. Let's look at how many digits 300,000 has. So that's 20,000. So we're going from 20,000 to 200,000. And so each one of these is going to have at least 20,000 digits. And we have to do 900,000 of these. So in terms of getting how many digits we have operations, I'd multiply 20,000 by at a minimum 900,000. If I go to the 500,000 mark, I've got 100,000 digits, and I have at least 500,000 like this. So if I take 100,000 and multiply by 500,000, it looks like it's 5 times 10 to the 10. And we have 1 times 10 to the 8 seconds. So are you still willing to take the deal? But what I'm saying is you would have to average better than 1 digit addition a second for 4 years by a significant amount. The number of seconds is of size 10 to the 8. The number of digits that you have to add is at least 3 orders of magnitude better than that. So you're really talking about doing 100-digit additions a second for 4 years straight. I will switch what I was going to do based on your confidence. All right, so this is a computer, I think, with a world record for solving a Rubik's Cube. It's like 0.3 seconds.
3, 2, 1.
Yeah, this is the computer, extremely fast. This is at 1/4 speed. It's having a little trouble. It's not correctly equipped. And this is 0.03 times speed. Yeah. This is around the level that a human could probably turn if you didn't even have to stop and think about what you're doing. Yeah. This is showing a decrease by a factor of roughly, I think, 33. And so I admire your optimism, but just looking at these numbers, and this is what you want to be able to do, you want to get order of magnitude estimates. Is this reasonable? Is it reasonable to do this much, 100 digits a second? It is just not humanly possible to do. There's a great quote, God is on the side of the heavier artillery. And you may pray as much as you like, but I will just bet on the side of the sheer magnitude of the computation. It's just not doable. It is just not doable by humans in this amount of time. But in Mathematica, it was able to do it pretty quickly. Now, here is a little code that we can quickly write. Let's say first to be 0. Be so what do you think this does? What do you think this code does? So we start off with the numbers 0 and 1. And then I form a new number and I add them. And then I change the value of the lower one to what was the upper one before. And then I change the upper to the new number I just got. What do you think this is going to generate? So I start off with 0 and 1. What do I get when I add 0 and 1? So the new number is 1. I now make lower equal to the one before, and the new is now 1. Now I have 1 and 1, I add them, I get 2. I make the lower the upper from before, which is 1. I make the upper the new number 2. Now I have 1 and 2, I add them, I get 3. I now make the lower number 2 and the upper number 3. What's this going to generate? So if I don't know the formula for the Fibonacci's, this will generate them. So yeah, to get a sense of how long this is going to take. So I'm going to calculate the first 10,000 Fibonacci numbers like this. So it took 0.01 seconds. So before, when I was doing things, it was instantaneous. The computer basically just had it. All right, let me do 100,000. 0.2 seconds. So even a naive computer, so long as it can hold very large digits in its memory, is able to do this. Let's see how long it would take to do 1 million. It was 0.2 before. Now you see this noticeable lag. It's going to be more than 10 seconds. It's getting worse. This was now 4.9 seconds to do the millionth Fibonacci number. I might as well just have this doing something in the background. You're allowed to torch your computers, just have the computer plunk away at this and see how long will it take the computer to do 10 million. Mathematica knows the formula for the nth Fibonacci number. This is the Binet formula I was telling you about. This is why it's so remarkable. You can jump to any term in the sequence. And so we'll come back later in the class to see how long it actually took. Just go back and continue with the lecture. All right, so it turns out we can write down explicitly the nth Fibonacci number as 1 over root 5, 1 plus root 5 over 2 to the n, minus 1 over root 5, 1 minus root 5 over 2 to the n. What's interesting is 1 minus root 5 over 2, that number is less than 1 in absolute value. So as you take it to a larger and larger power, it goes to 0. But 1 plus root 5 over 2 to the n, well, that number is greater than 1 in absolute value. So really, the nth Fibonacci number is whatever integer is closest to the first part of the expression. Right. So what I want to do is talk a little bit about ways to find Fibonacci numbers. So we have, fn plus 1 is fn plus 1 is fn plus fn minus 1, f0 equals 0, f1 equals 1. You read that fn plus 1 is less than equal to 2fn. My sequence is not decreasing. So this means it grows slower than 2 to the n. Every time I increase it by 1, I at most double it. Similarly, fn plus 1 is greater than or equal to 2fn minus 1. So every 2 will at least 2, so faster than square root of 2 to the n. Because if I'm going at the rate of square root of 2 iterations of root 2 would be 2. So I believe root 2 to the n is roughly at least n is bigger. When n equals 0, 1, this might be off by a little bit just because of the initial conditions. But very quickly, it's going to be growing at least as fast as root 2 to the n and slower than 2 to the n. So we're going to use the method of divine inspiration. Let's try fn equals r to the n. This gives r to the n plus 1 is r to the n plus r to the n minus 1. This is called the characteristic polynomial. If you bring everything over to one side, you can try to solve this. We get r to the n minus 1, r squared minus r minus 1 equals 0 like that. And so the roots are 0 and 1 plus or minus root 5 over 2. How did I get the 1 plus or minus root 5 over 2? What did I use? I used the quadratic. And then you just show if R1 and R2 are roots and solve the recurrence, so does C1 R1 to the n plus C2 R2 to the n for any C1 and C2. And if you think about it, if r to the n works, if I multiply that by 5, then it's going to work because every 2 gets multiplied by 5. So if r to the n works 5 times r to the n, negative 2 times r to the n. And if I have a sum of things that work, it's also going to work because I can just view each one separately. So I strongly encourage you to go through the calculation and show that if r1 and r2 work, then this works. And now, if we take n equals 0, we get C1 plus C2 equals F0, which is 0. If we take n equals 1, we get C1 R1 plus C2 R2 equals F1 equals 1. So we have 2 equations and 2 unknowns. So what do we get from the first equation? So from C1 plus C2 equals 0, what do we deduce? So what's the relationship between C1 and C2? If their sum is equal to 0, they're opposites. So the first one tells us that C2 equals negative C1. So the second equation becomes C1 R1 minus R2 equals 1, or C1 equals 1 over R1 minus R2, which when you do the algebra gives you 1 over 1. And this will give us Benet's point. So now we get Benet. Fn is 1 over root 5, 1 plus root 5 over 2 to the n minus 1 over root 5, 1 minus root 5. So we were able to solve this recurrence relation. And this idea of just trying r to the n, it works for a huge number of recurrence relations. As long as the characteristic polynomial has distinct roots, we get all the roots this way. If there are repeated roots, the subject is a little bit more complicated, but the goal today is to just give you a sense of how you attack this problem. Any questions on what we've done so far? All right, so let's see an application. So the first is this idea of a generator. So we've talked about series a lot in this class. I want you to see why we've spent so much time talking about two series converge. So I'm going to do something which seems absurd at first. I'm going to form a function which is the sum of fn x to the n, where the fn are the Fibonacci numbers. Well, if I don't know what the Fibonacci numbers are, how can I work with the sum involving them? But I do know what the Fibonacci numbers are. I know the initial conditions, and I know fn plus 1 is fn plus fn minus 1. So in some sense, I know the numbers. I just don't know that I know them. You know, if you wanted me to tell you one, and I know we have some wonderful confidence in the room today, you know, that, hey, you want the million Fibonacci number? I'll give it for you. I don't believe in that 1 year, 4 year confidence, but, you know, with enough time, you know, no doubt you can get it. The challenge is making sure you don't make a mistake as you go along. So let's just write down this function fn x to the n. This is one of the most powerful ideas in mathematics. It's not usually done at this level, which is, I think, a shame because it's nice for you to know what's out there. So now, I'm going to just play some games with this. And don't worry if you don't follow all the algebra. I'm not going to give you anything like this on the test. I just want you to have a sense of how you do problems like this. So I can switch my indices. I'm supposed to sum from n greater than 0. So n goes from 1 to infinity. Okay. Let me just start off related sum going from 2 to infinity. And I'll look at fn plus 1 xn plus 1. I'm going to express this in terms of g or things close to g. Well, because fn plus 1 is fn plus fn minus 1, I can substitute for fn plus 1. So now I have two sums on the right. Notice the first sum on the left looks a lot like g of x. It looks like g of x, but it's starting at what index? Starting at which index? Not 2. Not 1. I've got fn plus 1 x to the n plus 1, then it goes from 2 to infinity. What's the first power of x we get? 3. So this really looks like g of x minus f1x minus f2 x squared. If you look at the next term, the fn x to the n plus 1, for my g's, I want the index of f to be the same as the power of x. I have f sub n, but I have x to the n plus 1. What could I do? I want them to be the same. So how could I rewrite this? What substitute? I've already used the Fibonacci recurrence to substitute. So I've got to do an algebraic. I've got fn, and it's being multiplied by x to the n plus 1. What do I want it to be multiplied by? So how can I rewrite x to the n plus 1? How can you write x to the n plus 1? I want it to look like x to the n. So how could you pull out an x to the n? How can I write x to the n plus 1? think of your laws of exponents. Yeah, what could I pull out of x to the n plus 1? I could pull out x, right? This is just the same as x to the n times x. Pull out x. And now I have fn minus 1 x to the n plus 1. What would I want to pull out here? X squared. So I would write this as x to the n minus 1 x squared. Pull out x squared. And so when I do that, I now get x times fn x to the n plus x squared times fn x to the n. Well, these are very close to the function g. I just subtract what I need to. So for the first one, I subtract f1 and f2. For the second one, I just subtract f1. And for the third one, I don't have to subtract anything because the sum starts at 1. So I've played games to fix my summation so that the sum's all 1 from 1. I fix all the indices, so it's always fn x to the n. It's okay not to follow every step, but just want to say, okay, you play some games with sums, you get this relationship, and now we just solve for g. So g of x is unknown, and so we bring all the g's over to one side. And if you have trouble with algebra, I strongly urge you to go through and do all these calculations, and you get g of x is x over 1 minus x squared. So here's our generating function. Even though we don't know what the Fibonacci numbers are explicitly, they're just defined implicitly, we have a closed form expression for the generating function. You could try to expand this out using a geometric series. I could write this as x times 1 over 1 minus r, with r equals x plus x squared. If I try to expand, 1 over 1 minus r is 1 plus r squared plus r cubed plus dot dot dot. This is 1 plus x squared plus x squared squared plus x squared cubed plus dot dot dot. This is 1 plus x squared plus x squared plus 2x cubed plus x to the 4th plus x cubed plus 3 x to the 4th plus this is becoming a nightmare. The problem is different terms are going to interact. So if I want to get an x cubed term, a couple of different terms can give me an x cubed. Only finitely many, but it's going to be a while. Okay, we've got x over 1 minus x squared. We've done something in this class where we see something like this. What have we done? It's an integration technique. Not by parts. So by parts would be, u and r dv. It's something else though. It does have part in it with a few of the levels. It's the partial fractions. Oh my God, partial fractions actually have a use. It's not just for evaluating integrals. If I use partial fractions, I can write this, I can factor the denominator, and when I do everything, this is what you get when you do the partial fraction expansion. Now I can use the geometric series formula, and now everything is going to be really nice. And when I use the geometric series formula, I now get Binet. So this is a wonderful application of a lot of the stuff we've been doing. So you can use partial fractions for more than just integrating. And we get this explicit closed form expression that allows us to jump to any term. Okay, and you should have watched the video which talks about applications to gambling. So I'm not going to go through that now. There is a fundamental flaw. Do not do this strategy. So I want to talk about a following problem. So to make things simple, we're going to really adjust how wheels live. So we're going to make the following something. I'm always going to talk about a pair of wheels and not keep track of the different male and female wheels that get together to create new, I think it's cows. Yeah, to create the new cows. So I'm going to assume that time moves forward in a discrete step of 1 year. And I will assume all the wheels have babies at the same time. And then when it's your time to die, you all die at the same time. So when you're born, nothing happens for the first year. When you're 1 year old, each real pair gives birth to 2 new pairs of wheels. If you're 2 years old, you give birth to 1 pair of wheels. And no other values give birth to wheels. And everybody dies when you turn 4. Okay? In this very simplified model, yes. Very simplified, yes. And they all die at the same time, on precisely the same day. It's amazing. Biologically, you could argue that once the wheels are done reproducing, they might actually have no involvement in this model and don't really matter. Unless the older wheels are somehow protecting the younger wheels from predators. There's a lot of great conversations in evolution as to if you are no longer involved in your offspring after they're born, how much anyway. So I want to try to estimate how many whales are there going forward in time. Do you think the whale population is increasing or decreasing? So you live until 4. Each pair gives birth to 2 new pairs after 1 year and 1 pair after 2 years. Yeah, increasing. How many new pairs of whales does 1 pair provide? 3. Okay, this should be a massive population increase. And so what we're going to do is we're going to set up a recurrence relation. We're going to let A and B and C and D n represent how many wheels we have at time n that are 0, 1, 2, or 3 years old. Why don't we have to consider how many wheels are 4 years old? They all die. So we're not going to bother counting them because they immediately die. Okay? So what I want to do is I want to figure out recurrence relations to describe how many wheels will there be at time n plus 1 in terms of how many wheels there were at time n. So we have an plus 1 plus your bn plus 1, cn plus 1, and dn plus 1. So let's try to do, which one do you think is going to be the easiest to figure out? How many wheels were born, or how many wheels are 1 year old, or 2 years old, or 3 years old? Sorry? Well, no, because this is 0, 1, 2, 3, dead. So which do you think is the easiest to figure out how many wheels are born in time n plus 1, or how many wheels are now 1 year old in terms of how many wheels there were of each age group one year before? How would you have a wheel who's 1 year old in year n plus 1? What must they have been in year n? 0. So bn plus 1 is what? The number of wheels of age 1 in year n plus 1 is what? What would it be in terms of the wheels of the previous year? If you're 1 year old in 2022, how old were you in 2021? 0. So the population of 1 year olds is what in terms of A N, B N, C N, and D N? Sure, Bn plus 1 is how many wheels are 1 year old in year n plus 1. We've just said that that's equal to the number of wheels that was 0 in year n. How do we denote the number of wheels that was 0 in year n? That's an. So it's just going to be 1 times an plus 0 times bn plus 0 times cn plus 0 times dn. How many wheels are 2 years old in year n plus 1? Bn. So it's going to just be 0 times an plus 1 times bn plus 0 times cn plus 0 times dn. And similarly, the ones that are dn plus 1 would just be 1 cn. So the an is the harder one. How many wheels were born in year n plus 1? Well, any wheels that were 1 year old will generate 2 new pairs. So nobody who was just born is going to do anything. The 1 year olds will give you 2 pairs. The 2 year olds will give you 1 pair. So we have a system of occurrence relations. So if I give you the initial conditions, you can just write an Excel sheet with your columns A, B, C, D, and just go through. You can also create a way to solve this similar to the Fibonacci. I'm not going to go into all the details of how you would do that. I just want you to know this can be done. And what you could do, of course, is you can make this a little bit more reasonable. You could say, I'm not going to assume that everybody dies in year 4. Maybe what I'll do is 98% of the people will live 1 year and only 2% die. So I'll replace this one with 98%. And then maybe of the people who live, maybe this would be 88%. And maybe this would be, I could do something like that. Or I could do more randomness. I could have this as a random variable drawn from maybe 0.95 to 1. And then the number of pairs one could also be a random variable, maybe centered at 2. And then this becomes a much more involved process. I could then also introduce predators. And then the predator population might be growing based on the number of whales. And there's a beautiful series of differential equations to model human population where we're going to, we're here seen Avenger movies. Okay, so I don't want to give anything away from who haven't seen the Avenger movies, but there could be too many people and it could cause the population to explode to the point where humanity is destroyed. So benevolent aliens come down to Earth and start harvesting us. What rate should they harvest us so that we don't overpopulate? And there's real potential. When you look at some forest fires, a lot of forest fires come from too many trees. And then when there's a small fire, there's so many trees nearby that it spreads. There was actually a controlled burn. Yeah, I was going to say, I'm working this into the class. There was a controlled burn. We've actually had uncontrolled burns in the past few years here. And when we came back to our house yesterday and we saw the firelight, although the firelight looks pretty straight, you would expect a little more jagged if it was. So we were hoping it was a controlled burn. So if we try to use some vector notation, if we let Bn be An, Bn, Cn, Dn, and we let A be this transition matrix, then we can actually write down what we were doing as Vn plus 1 is A to the n plus 1 V0. And we can use this to successfully model what's going on. And so what we're really doing is Vn plus 1 was just A times Vn. But Vn is A times Vn minus 1, right? So Vn plus 1 is A squared times Vn minus 1. Will then become A cubed Vn minus 2. And you see, okay, I have A times Vn, 1 plus n is n plus 1, A squared Vn minus 1, it's again, adds up to n plus 1. So if I want to go all the way down to V0, it would be A to the n plus 1 V0. And so now, if I can calculate what a high probable matrix is, so shifting back to Mathematica, I'm going to have to toggle quite far down because it calculated the Fibonacci. So let's let A equal 0, 2, 1, 0 is the first row, right? Next row is 1, 0, 0, 0, then 0, 1, 0, 0, and then 0, 0, 1, 0. So here's A. So let's go A. So let's try. That looks much better. Right. This would be 100th. It turns out that there are, to compute this efficiently, it starts to get a nightmare when I start looking at it. But there are formulas that would allow you to write the 100th matrix as a diagonal matrix by changing your coordinate systems. So I think we've talked a little bit about ellipses in this class. If the ellipses are aligned with the coordinate axis, it's easy. If they're not aligned, just rotate back. That's what you do for a matrix like this. It turns out you can diagonalize this matrix by changing your coordinate system, and now calculating Q powers becomes very easy. So the whole goal of this is to just give you enough of a sense of what can be done with what you're learning. And so what we've done here is we've shown we can actually model some real world problems using just these finite difference equations. Tomorrow, which is Wednesday, we will do a similar thing. We will do it for differential equations. Talk about how would you model something where things can vary continuously. And again, this is the goal of why you're learning calculus. Calculus allows you to discuss how things change. We could do things that change discretely, which is fun. It's a lot easier when things change continuously because now we have all the tools of calculus at our disposal. And so when you're doing this, you're going to have to solve equations. So there's a reason why we're teaching you all these techniques on how do you solve equations. The goal is not to solve cookbook problems in exams. We need to do that, but that's not the goal. The goal is I want to model something. And one of the most famous examples of things that people model is like the predator prey, the rabbits and the foxes. What happens as the rabbit population goes up? More food for the foxes, which is good for the foxes. So the fox population goes up. What happens as the fox population goes up? Rabbit goes down. And if there are too many foxes eating too few rabbits, the rabbits eventually reach the point where they die out. And then what happens to the foxes? They die out. So you have to be extremely careful when you look at this, that sometimes, the correct solution for some of the foxes may not be to eat rabbits, but to eat each other. And so you have to be, there's a lot of really interesting population dynamics you can do. And this is just one of many different situations. All right, so this is a good place to stop for today. And we will continue with applications on